Set the real stakes plainly. You can't get an exact area from a curved edge by just multiplying two straight lengths. So how do you get an exact number, not a guess, when one side of your shape bends? Keep that riverbank plot parked. We will come back and solve it once we have the tool. Hold here and ask directly. If you only trust rectangles and triangles, what's your plan for a wobbly curved edge? Chop it into strips. Chop the strip under the curve into a few equal rectangles and add up their areas. You get a number close to the true area, but look at those gaps at the top of each strip. It's not exact yet. Now make the strips thinner and thinner. The gaps vanish and the running total locks onto one exact number. That settled number I, the exact area under the curve, and that is the whole idea behind this new tool, the definite integral. You evaluate it the fast way. Find the antiderivative, plug in the top value, plug in the bottom value, subtract, and it matches the strips exactly every time. Onto the shelf. The definite integral, the antiderivative evaluated at the top limit minus the bottom limit. Watch what happens when the curve dips under the line. The rectangles flip below the axis, so the sum you get back is negative. That's the definite integral being honest about direction. But an area you would actually measure on the ground is never negative, so you take the size of that number, not its sign. Onto the shelf. When the curve dips below the axis, the area is the magnitude of the integral, never the raw negative. Unpark that riverbank plot time to solve it for real. Close the loop out loud. Run that exact same tool on the real river boundary, and instead of an eyeballed guess, the surveyor now has one exact number for that plot. No ruler and no leftover rectangles, just the exact area. When the boundary is a curve A, N, D aligned together, first find exactly where they cross. That tells you where to start and stop. Then it is always top minus bottom, integrated between those two crossing points, nothing else. Onto the shelf. Area between a curve and a line, top minus bottom, integrated between their crossing points. The curve y equals x2 minus 4x is defined for 0 is at most x is at most 4. Part A. Evaluate the definite integral of y with respect to x from x equals 0 to x equals 4. Part B. State the area of the region enclosed between the curve and the x minus axis over this same interval. Find the antiderivative first. X cubed over 3 minus 2x squared. Evaluate at the top limit, x equals 4, minus 32 over 3. Evaluate at the bottom limit, x equals 0, 0. Subtract. The definite integral is minus 32 over 3. Check the sign. Y equals x times x minus 4, which is negative for every x between 0 and 4, so the curve sits entirely below the x-axis, exactly why the integral came out negative. Area can never be negative, so the enclosed area is the magnitude of that value, 32 over 3 square units. Part A, the definite integral of x2 minus 4x from x equals 0 to x equals 4 is minus 32/3, negative because the curve lies entirely below the x-axis on this interval, confirmed by y equals x times x minus 4, which is less than 0 for every x between 0 and 4. Part B. The area of the enclosed region is the magnitude of that value, 32/3 square units. Find the area of the region enclosed between the curve y equals x2 and the straight line y equals 2x. First, find where they meet. X squared equals 2x gives x equals 0 or x equals 2, meeting at 0, 0 and 2, 4. Check which one is on top. At x equals 1, the line gives 2, the curve gives 1, so the line sits above the curve throughout. Method 1, the direct way. Integrate top minus bottom, 2x minus x squared from 0 to 2. That gives 4 minus 8/3, which is 4/3. Method 2, an independent check. The triangle under the line has area 4, the area under the curve is 8/3, and 4 minus 8/3 also gives 4/3. Both methods agree exactly. The curve y equals x2 and the line y equals 2x meet at 0, 0 and 2, 4, with the line above the curve throughout that interval. The area of the enclosed region is 4/3 square units, confirmed two ways. Directly by integrating 2x minus x2 from 0 to 2, and independently by subtracting the area under the curve 8/3 from the triangle under the line 4. That curved riverbank plot, no ruler, no eyeballed guess, came out to exactly 18, because a curved boundary is exactly when you reach for this tool. Whenever you're asked to evaluate a definite integral, find the area under a curve, or find the area of a region bounded by a curve and a line or two curves. First, find the antiderivative, then evaluate it at the top limit minus the bottom limit. If that number is negative, the region lies below the x-axis, so the actual area is its magnitude. And if the curve crosses the axis inside the interval, split it into pieces first and take the magnitude of each piece. If the region is trapped between a curve and a line, find where they cross to get your limits, check which one is on top, then integrate top minus bottom. This exact technique is what 3.4 reuses to find a volume, once that same area is spun into a solid.